9.3 Quadratic Inequalities in two variables. We're going to warm up with graphing some quadratics. So the first one here, y equals x squared minus 2x minus 3. We want to label the vertex, the y-intercept, and the zeros. So let's first find the zeros by factoring this. Looks like we can factor it into x minus 3, x plus 2, x plus 1, I mean. That means that our x-intercepts are at 3 and negative 1. So we'll first mark those 3 and negative 1. We want the y-intercept. That would be this value right here. It's always the constant value when it's written in this form. So negative 3 is our y-intercept. That's not our vertex. Our vertex is going to be halfway in between negative 1 and 3. So halfway in between is 1. So vertex is at x equals 1. Let's use that value in the equation to find the y value of the vertex. And it looks like it's negative 4. So the vertex is at 1, negative 4. Now we can add some more points here, and you can get those from a table of values. And last, we want to actually draw the parabola. Something like that. Okay, next one. I want to graph this one. This has got a negative leading coefficient. So the first step I'm going to take is to factor out the negative. It's just annoying, and it increases the likelihood of making mistakes, I find. We'll get rid of it there. And now we can factor this into 2x and an x and a 3. It looks like that will be plus and that will be a minus 1. So there we go. Our x-intercepts are at x equals 1/2 and negative 3. We'll plot those points on the graph, 1/2 and negative 3. Now we'll find our y-intercept. That'll be this constant term here of 3. So there's our y-intercept marked on the graph. Which would mean, given symmetry, that's also a point on the graph. 1/2 units away and 3 units up. Now we need to find the vertex, and it's halfway in between this. That's a bit messy, so I'll complete the square to find the vertex. But you could use a graphing calculator or use the method we did first, find the point halfway in between, and use that in the equation. Okay, so first when we complete the square, we want to factor out the leading coefficient, and that becomes the bouncer in the front. Next, just out of the first two terms there, plus 5/2x, leave space for our house guests 1 and 2, close our house, leave our awkward uncle in the backyard. Next, we want to figure out who's the perfect house guest. That would be half of this, so 5/4 squared. So 5 squared is 25 and 4 squared is 16. And he brings his negative friend. Now, we want to get rid of that negative friend. He's going to ruin the perfect house party. So we use the bouncer to kick him out. So negative 2 times negative 25/16 becomes positive. So in this case, he likes going out to the backyard, plus 25/8. And so that we can add these, let's convert a 3 into a mixed fraction with the same denominator as 8. So 24/8. And then we just need to factor our perfect square trinomial here, x plus, and it's always half of this term here, 5/4 squared plus 49 over 8, and that's a bit awkward to graph, so that is the same thing as 6 and 1/8. So now we know where the vertex is that it's at negative 1 1/4 and 6 1/8. So about there. And now we can draw our parabola. Something like that. 9.3 quadratic inequalities in two variables. It can look like any of these, greater than, less than, greater than or equal to, or less than or equal to. Of course, these could be in factor or vertex form. They don't have to be in standard form, but we could always make them like this. A quadratic inequality has two dimensions, x and y, and so we can represent the solution region on the Cartesian plane. And then we can shade in an area and show that all the points that in the shaded region are coordinates that will satisfy this inequality. Example 1, we want to graph y is greater than x squared minus 2x minus 3 and determine if the point 2, 1 is a solution. So first we'll graph this. We can factor x squared minus 2x minus 3 and find the x-intercepts to help us graph it. Looks like the x-intercepts are at 3 and negative 1. The constant term is negative 3, so that's our y-intercept. And I know there's symmetry, so this will also be 3. There's no stretch. Our a value here is 1, so I know that the vertex is just one more unit down. So this goes over 1 up 1, over 2 up 4, over 3 up 9. You can use that, or you can use a table of values and find those points. Let's connect these points here with a dotted line because it's just greater than. So I'll try to dot this. Don't want a solid because it's not greater than or equal to. And we want y is greater than, so we're looking at all the y values that are above the dotted line. So this is our solution region in here. And we could use the test point to confirm that we did, in fact, shade in the correct region. So it looks like 0, 0 is in our solution region. So I could put 0, 0 in here and see if it works. So 0 is greater than 0 squared minus 2 times 0 minus 3. 0 is greater than negative 3, because those two are just 0. So that's true. So we've shaded in the correct region. And last thing, is 2, 1 a solution to the inequality? So now we can just find 2, 1. Is it a solution? Yes. 2, 1 is a solution. Now, we could have just tried 2, 1 in the inequality directly, and that would have worked as well. Example 2, we want to graph y is less than or equal to negative 2x minus 5x plus 3. Now this is a similar quadratic to what we had in the warm-up. So when we find the vertex, I'm just going to take it from there. Find the x-intercepts, we could do that by factoring this again. And we had 2x minus 1 and x plus 3, so our x-intercepts are at 1 half and negative 3. Our constant term here gives us the y-intercept, so that would be 3. And then the vertex, again from the warm-up, was negative 1 1/4 and 6 1/8. That would be that point there. Right now we are less than or equal, so I can draw a solid line here for this quadratic. And shade the appropriate region, y is less than, and so take this point here for instance, and I want to go less than, so down here. So I want all the y values that are down here. Now you might say last time it was inside the parabola and this time it's inside the parabola. So let's just flip back and look at the last slide. This one is greater than and it's inside the parabola. This one's less than and it's inside the parabola. I don't want you to think about inside and outside the parabola. It's a bit confusing because it changes. When you have less than, take a point and go down from there, and we're shading below. So it's always above and below. Now last thing, determine if 2, 1 is a solution. 2, 1. So no, 2, 1 is not a solution because it's outside the solution region. Example 3, we want to know what is the inequality shown on the graph below. Now we have a dotted line and we're shading below this parabola, so we know this is going to be y is less than. Now we have the vertex, so we can write this equation in vertex form. We also have the x-intercept, so we could write this in factored form. So let's do vertex form first. This is some a value x minus p squared plus q. Now our p and q represent our x and y values of the vertex respectively, so let's put those in. So our x value of the vertex is -2 and our y value is 4. What about the a value? Well, we can look at this and say this went over 1, down 1. Normal parabolas that aren't stretched, they would be over 1 and up 1, so we know this just got reflected down. And there's our inequality for this graph shown here. We could also do it in factored form using the same a value, and our factors would just be, well, this one's x minus 0, so I'll write that first, but I'm not going to leave it like that, and x minus -4 minus -4. And then we can just tidy this up a bit, because x minus 0 is just x, and x plus 4. And so we've got this vertex form or this factored form, and they look different, but they are in fact representing the same thing here. Example 4, what is the inequality shown on the graph below? Now for this one we have the x-intercepts at -7 and 3, but we don't have the vertex clearly. I don't want to take a guess, that's unknown. So we'll use factored form, it's not a problem, and start off with y. Now we've got a solid line and we're shading below that solid line, so we want all the y values that are less than or equal to this parabola. Now we'll write it in factored form, so x minus our x-intercept, which is -7. Next one, x minus our other x-intercept, which is 3. Now we need to find this a value here, and we're going to do that algebraically by picking a value that we know here, a point that we know. How about 1, -4? It looks like it's on the parabola. So we using 1, -4. We want to find that a value for this parabola. So I don't know a, so I'm leaving it as a. And then I'm putting in 1 for x and -4 for y. Then we've got 8 times -2. We've got -16. Divide both sides by -16. Looks like a is 1/4. So we come back here and we use that a value in the inequality 1/4 or 0.25 if you prefer. And there is our inequality that's shown on this graph. Example 5 is our word problem. A satellite dish is 60 centimeters in diameter and 20 centimeters deep. We're going to put that on a graph here. And we want the center of the parabolic cross-section at the origin. So that means we're going to be looking at our dish sort of cut in half here. And it ends there and there. The satellite dish does not continue on forever. Now the dish is 20 centimeters deep and 60 centimeters across, so that means that this would be negative 30 and this will be 30. We want to determine an inequality that shows the region from which the dish can receive a signal. Now that's up here. The dish could receive a signal anywhere above it, and so let's try to create an inequality to represent that. First, let's get the equation of the parabola here. So let's go y equals some a value. We could do vertex form, 0, 0. So that would be x plus 0 squared plus 0. Let's tidy this up a bit before we go on. It's just y equals x squared. What's the point we know? Well, we could use this point right here, 30, 20. And that would be 900a. Divide both sides by 900, and we get that a is 1 over 45. Now let's make our inequality. Y is greater than 1 over 45 x squared. We'll say if the signal originates inside the satellite dish material, then we can't receive that signal because it's already there. So we'll just say greater than. And that's it. This was part of Relations and Function 7, solving problems that involve linear and quadratic inequalities in 2 variables. Here's some homework. Have some fun.
Oh yeah. Oh yeah.